This stuff is nuts.
Let's start out with our circular disc with a diameter of 1 meter and with a hole in the middle of 10 centimeters and with a thickness of 1 centimeter. And the gremlin told us it's aluminum.
Nope.
And a couple of properties that we might want to know about aluminum. First of all, aluminum's density is equal to 2770 kilograms per meters cubed. And specific heat for aluminum is 875 joules per kilogram degree C. Now, if we look at the amount of energy generation that we've added to this, now in this problem, we specified an internal heat generation and that was equal to some number like, say, 100 watts per meter cubed. Now, that's actually 100 joules per second meter cubed. If we figured out how much total energy that we had in this, we would say that the total change in energy I'm going to call that little u, which is watts per meter cubed. And multiply that by the volume, which is meters cubed, and multiply that by the time, which is seconds, then that would give us an answer that's in joules. That is also equal to Cp times the mass delta T. So we can go from that and say that little u times the volume times time is equal to Cp delta T times the mass. So if we're interested to find out how big a delta T we might have, we could look at this and we could say that we've got the internal heat generation times the volume times the time divided by Cp for the material and the mass. Now the volume over the mass is just simply equal to 1 over the density, because that's in kilograms and meters cubed. So we can eliminate that and we can just simply look at the internal heat generation times the time, Cp times density. And so if we're looking at an internal heat generation of 100 and we look at 300 seconds and we're saying Cp is 875 joules per kilogram degree C and density is 2770, then that should tell us that our change in temperature should be about 0.012 degrees C. Now we could look at this a different way, and we could say, in addition to that Cp delta T, we're also losing heat. And our heat loss is the thermal convection coefficient times the area times the difference in temperature from the body to the surroundings. So if we assume that H is approximately equal to 10 watts per meter squared per degree C, and if we say that area is equal to pi over 4 d squared times 2, because it's top surface and bottom surface, and if we neglect the perimeter, then that area for a 1 meter disk is going to be about 1.57 meters squared. And that's neglecting the whole. So from this, we could say that delta U is going to equal H A delta T times time. And we could say that if we want to heat up by 1 degree, then how long will that take us? Or how much energy would we require to heat up for 1 degree? So we could say that what will our steady state delta T be in this case? And we know from our conditions that our delta U, and that's multiplying by the volume, and the volume is equal to 0.007, and that's all divided by H, which is 10, and time is in watts, and area was 1.57. So that means our change in temperature, so our steady state temperature, just looking at the heat loss, is 0.005. Looking at the energy input, oh, that's really great. It's so nice to be able to make some sense of it. Now that we've done a hand calculation and seen that the expected steady state conditions, just using a really simple calculation of the bulk energy input to the plate and the bulk heat loss, we found that we should be expecting 0.05 degrees C or so. So let's take another look again at the results and see how they look. Yeah, I don't get that. So here's the steady state results that I showed in one of the previous videos. And you can see that in this steady state solution, my maximum temperature difference was 0.049, which is less than the simple calculation, but that's okay because it was simple, but absolutely in the right ballpark. So that gives me some confidence. Now, cool. Let's have another look at the unsteady simulation. So here's the transient results that we had seen before, and looking at the temperature. If I simply play, then that's kind of slow and interesting. But you can see that in the unsteady condition, it doesn't go to 0.05, it only goes to 0.01, but this is only 300 seconds. Now, we could have refined the calculation we did by hand and looked at how long it might take to get to 0.05. But in our unsteady calculation for 300 seconds, just by hand, simple calculation, we got an answer of 0.012 degrees C as the temperature difference. And look what our simulation showed, 0.011. This stuff is nuts. So this gives some confidence that this model that we've created in ANSYS is at least in the right ballpark. Now, the hand calculation can't get us much more than that, but it did give us a pretty good hands-on idea of whether or not our simulation was realistic. And it was. So what happens if we don't use the whole plate?
Nothing good happens, that's for sure.
What about symmetry?